Black holes are among the most intriguing phenomena in space, often portrayed in popular culture as cosmic monsters capable of devouring everything in their path. A prime example of this portrayal is the film Interstellar, where black holes are depicted with a mix of scientific accuracy and creative imagination. So, what exactly is a black hole? At its core, a black hole is a region in space where gravity is so intense that not even light can escape its grasp. This extreme gravity occurs because the black hole's mass is concentrated into an incredibly small space. This leads to the formation of two critical features: the event horizon and the singularity. The event horizon is the boundary surrounding the black hole. It's the point beyond which nothing can escape. The singularity, on the other hand, is the central point where gravity becomes infinitely strong and the curvature of space-time is infinitely warped. Black holes themselves are invisible because they don't emit light, making them detectable only through their interactions with nearby matter and light. To understand black holes better, we need to get into Einstein's theory of relativity. This theory revolutionized our understanding of space and time. Einstein's special theory of relativity, introduced in 1905, tells us that the faster an object moves, the slower time passes for it relative to a stationary observer. Imagine traveling in a spaceship at near light speed. Time would appear to slow down for you compared to someone who stays on Earth. This effect is known as time dilation. Einstein's general theory of relativity, published in 1915, extends this idea by describing how gravity affects time and space. According to this theory, the presence of mass warps the fabric of space-time, causing time to slow down in stronger gravitational fields. This warping of space-time is particularly pronounced near black holes. The closer you are to a black hole, the more time slows down compared to someone further away. This phenomenon was dramatically depicted in Interstellar, where a planet close to a black hole experienced 7 years of time for every hour that passed. Black holes are not born from nowhere. They're formed from the remnants of massive stars. Stars, including our Sun, generate energy through nuclear fusion at their cores, which creates an outward pressure that balances the inward pull of gravity. When a star exhausts its nuclear fuel, this balance is disrupted. For stars with masses much greater than our Sun, this imbalance leads to a spectacular explosion known as a supernova. The core of the star then collapses under its own gravity. If the remaining mass is sufficient, it condenses into a black hole. For smaller stars, they end their lives as white dwarfs or neutron stars instead. White dwarfs are remnants of smaller stars that have shed their outer layers and left behind a dense core. Neutron stars, which are more massive than white dwarfs but not quite enough to become black holes, are incredibly dense objects formed from the collapse of more massive stars. The Chandrasekhar limit, established by astrophysicist Subrahmanyan Chandrasekhar, states that if a star's mass exceeds about 1.4 times that of the Sun, it cannot remain a white dwarf and will instead collapse further into a neutron star or a black hole. The process of black hole formation is a dramatic one, with the remnants of a star being compressed into an incredibly small space, creating a region where gravity is so intense that it becomes impossible for anything to escape. This is why black holes are such captivating objects. They challenge our understanding of physics and our perception of the universe. So, what would happen if you fell into a black hole? The answer is not entirely clear, as this is still an area of active research and speculation. You'd encounter the event horizon, where gravity becomes so powerful that escape is impossible. Beyond this point, the intense gravitational forces would stretch and compress anything falling in, a process known as spaghettification. Whether you'd be disintegrated or encounter a mysterious singularity remains one of the greatest questions in modern astrophysics. Black holes come in several types, each formed under different circumstances and varying greatly in size. The most common type is the stellar black hole, which forms from the collapse of massive stars. When a star exhausts its nuclear fuel, it can no longer support itself against its own gravity and implodes, creating a black hole. These stellar black holes typically have masses ranging from a few to several tens of times the mass of our Sun. In contrast, primordial black holes are hypothetical and thought to have formed in the early universe. These are not just small in physical size, but also incredibly dense. Their mass could be equivalent to that of a mountain or even a city, but they would be as tiny as an atom. Although these black holes are still theoretical and have not been observed, they represent an intriguing area of research. Then there are supermassive black holes, which are found at the centers of galaxies, including our own Milky Way. These black holes are truly colossal, with masses ranging from millions to billions of times that of our Sun. For instance, the supermassive black hole at the center of our galaxy is known as Sagittarius A. Scientists believe that every major galaxy harbors a supermassive black hole at its core, playing a crucial role in galactic formation and evolution. Another intriguing category is intermediate black holes. These are theorized to exist somewhere between the sizes of stellar and supermassive black holes. Despite their theoretical status, researchers speculate that these black holes might bridge the gap between their smaller and larger counterparts, though direct evidence for their existence is still lacking. Observing black holes presents unique challenges because they do not emit light themselves. However, we can study the material around them. This material forms an accretion disk, a swirling ring of gas and debris that becomes extremely hot and luminous as it spirals into the black hole. The accretion disk emits intense radiation, allowing us to detect the presence of a black hole indirectly. One of the most groundbreaking achievements in black hole observation came in 2019 with the first ever photograph of a black hole. This image, taken by the Event Horizon Telescope, captured the shadow of a black hole and its glowing accretion disk. The photo shows a bright, ring-like structure around a dark center, with the bright side appearing more luminous. This brightness variation is due to the Doppler beaming effect, where material moving toward us appears brighter than the material moving away. The image also reveals an optical illusion created by the black hole's gravity. Light bending around the black hole can make the accretion disk appear as though it surrounds the black hole in a more three-dimensional way than it actually does. This effect demonstrates the powerful gravitational influence black holes exert on their surroundings. Now, what happens if you were to fall into a black hole? As you approach the event horizon, the boundary beyond which nothing can escape, the experience would be anything but ordinary. The event horizon is the point of no return. Once crossed, not even light can escape the black hole's grip. If you were to cross this boundary, you would encounter extreme gravitational forces. This would lead to a process known as spaghettification, where the difference in gravitational pull between your head and feet would stretch and compress your body into a long, thin shape. Imagine being pulled apart like spaghetti due to the intense tidal forces. Inside the event horizon, the concept of time becomes distorted. To an outside observer, you would seem to slow down and fade away as you approach the horizon, while from your perspective, you might see the universe outside accelerating in time. This bizarre experience raises questions about the nature of time and space. At the center of a black hole lies the singularity, a point where gravity becomes infinitely strong and space-time curvature becomes infinite. Here, our current understanding of physics breaks down, and traditional laws of nature no longer apply. The singularity represents a fundamental limit to our knowledge about black holes. Looking ahead, black holes are not eternal. They can eventually evaporate through a process known as Hawking radiation. This phenomenon, proposed by physicist Stephen Hawking, suggests that black holes emit radiation due to quantum effects near the event horizon. Over incredibly long timescales, this radiation causes the black hole to lose mass and gradually shrink. As a black hole loses mass, it heats up and emits more radiation. When it becomes as small as an asteroid, it emits heat equivalent to that of our sun. In its final moments, a black hole can release energy comparable to billions of nuclear bombs in a dramatic explosion. However, this process is incredibly slow, and the largest black holes might take longer than the current age of the universe to fully evaporate. Well, we can say black holes are not the cosmic vacuum cleaners once thought to be gulping everything in their path. Instead, they're complex objects that challenge our understanding of the universe. They come in various forms, from stellar to supermassive, and each type reveals different aspects of their enigmatic nature. While the exact fate of an object falling into a black hole remains one of the universe's greatest mysteries, ongoing research and observations continue to deepen our understanding of these fascinating cosmic phenomena. What do you think happens inside a black hole? Share your thoughts in the comments below. And if you want to know about the mysteries of space, don't forget to watch our video on wormholes, the key to interstellar travel. See you in the next one. Bye.